Hello, and welcome to this presentation on op-amp precision. Op-amps, VIO, input offset voltage. Today, sensors are everywhere. In our modern world, we need to constantly measure everything: weight, UV, temperature, speed, current. Even though we live in an increasingly digital world, many sensors are still purely analog. And generally, most of them provide an extremely small signal. The question is how to deal with this low signal in order to transfer it to the digital domain without adding any error that could compromise the information. The solution is to use an op-amp to amplify the signal. But this op-amp would need to be ideal to not introduce any offset. Unfortunately, this kind of device does not exist. Op-amps will always impact measurements. However, by choosing the right op-amp, we can limit the error on the output as much as possible. In the example shown in this slide, let's consider a battery delivering a maximum current of 140 milliamps through a shunt of 10 milliohms. The resulting voltage will be 1.4 millivolts maximum. As the LSB of the ADC is 880 microvolts, we clearly need to amplify the signal to increase the accuracy. The main goal of this webinar is to identify which op-amp parameters are the most relevant in regards to precision. The main limitations to precision in analog integrated circuits are noise and mismatch. Before we start, let's define a few terms. What is offset? When a zero differential input voltage is applied, the op-amp output voltage should be zero. In practice, this is not the case. The offset voltage, by definition, is the differential input voltage that is required to make the output voltage zero. The input offset voltage parameter, generally called VIO, is defined as a DC voltage between the non-inverting and the inverting input. It is always specified in the electrical characteristics of a datasheet. It can be positive or negative. The VIO value will be different for each op-amp, and to ensure good precision, it is important to choose the op-amp with the lowest VIO because the VIO will be amplified by the gain and added to the total output voltage as an error. Some op-amps with a chopper architecture, like ST's TSZ121, exhibit a VIO of 5 microvolts. They are especially good for precision DC measurements. The cause of the input offset voltage is well known. It is due to the inherent mismatch of the input transistors and components during fabrication of the silicon die, and the stress placed on the die during the packaging process, a minor contribution. These effects collectively produce a mismatch of the bias of the input circuit, resulting in a differential voltage at the input terminals of the op-amp. For CMOS technologies, this equation shows the root cause of the input offset voltage. We can see that the size of the MOS width and length and the doping substrate play a key role in the VIO error. The resulting expression contains 4 terms. Since all of them can be positive or negative, they never all add up. Thankfully, this never occurs in practice. They never cancel each other out either. In any case, regardless of the design or process effort, there always remains a small input offset voltage. This also explains why for a dual amplifier, where 2 op-amps are in the same package, the input offset voltage of both channels is different. Let's now look at how the input offset voltage can impact the theoretical measurement of an application. Shunt current sensors are used in precision current sources for feedback control systems. They are also used in a variety of other applications, including battery fuel gauging and torque feedback controls in electric power steering and precision power metering. In this slide, we will look at a motor control application. Thanks to the H-bridge, the motor can be driven in both directions. The current measurement helps to know the motor's speed and its rotation direction. In such applications, it is desirable to use a shunt with a very low resistance to minimize the series voltage drop. This wastes less power and allows the measurement of high currents without a significant voltage drop. A typical shunt might be 0.1 ohm. The lower the current, the lower the resulting voltage through the shunt resistor. So at high current, the VO of the op-amp has little impact. For low current, it may become critical. When the current is only a few amps, the shunt's output signal is only a few hundred millivolts. For example, at 1 milliamp, the voltage through the shunt is 100 microvolts, to which the VO has to be added. So the op-amp demands a very low offset voltage and drift to maintain absolute accuracy. The op-amp is used as a differential op-amp in order to amplify the voltage drop appearing through the shunt resistor. In this example, the signal is amplified by 1000. With an ideal op-amp, VO equals 0 millivolts. So only the first term of the equation is valid. Normally, we read an output voltage of 100 millivolts. But as we said previously, the world is not perfect and the ideal op-amp doesn't exist. If we use a TS507 op-amp with a maximum positive VO of 100 microvolts at ambient temperature, we can see that the output voltage is minus 100 microvolts. This is far from the expected value of 100 millivolts, meaning that the speed information is completely incorrect. Moreover, this negative output will indicate to the MCU that the motor is rotating in the reverse direction, which is totally incorrect. Here, we can see how the VO of the op-amp can impact the entire application if the op-amp is not chosen carefully. If we use a precision amplifier with a chopper architecture like ST's TSZ121 with a VO of 5 microvolts at ambient temperature, we can see that we will make an error of 5% on the motor speed, which is really acceptable when we use a gain of 1000. If the motor rotation direction is changed, the theoretical output value considering an ideal op-amp will be minus 100 millivolts. We can see by using the TSZ121 that even in a reverse rotation, the measurement remains valid with only 5% error on the output. An op-amp's VO can be either positive or negative. This table summarizes the real impact of the VO with two different amplifiers, TS507 and TSZ121. With the TS507 and a positive VO of plus 100 microvolts, the result on the output is completely incorrect, even in regards to the motor's speed and rotation direction. If the VO is negative, the rotation direction of the motor is okay, but we make an error of 100% on the motor speed. Unfortunately, we cannot predict the polarity of the VO from one part to another. So when we make a design, it is important to take into consideration the fact that the VO might be positive or negative. However, by using the TSZ121 op-amp, which is a precision amplifier with an extremely low VO, the impact on the output result will be limited. The fact that the VO can be positive or negative will not impact the expected results. Another point we need to understand is the real impact of the VO on an application in terms of effective cost. The VO also reduces the dynamic range of an ADC. The loss of dynamic range affects the resolution of ADC circuits because the maximum dynamic range is required for maximum resolution. This table shows the equivalent resolution of the ADC for various input offset voltage ranges. Usually an op-amp can be chosen with a VO low enough to meet the desired accuracy. It is easy to find an op-amp that meets the VO specification for an 8 or 10-bit converter, but it becomes increasingly difficult as the resolution increases. We can see that if the op-amp is not chosen carefully, all the money spent on a 12-bit ADC is lost. Effectively, in this example, if the TS512 op-amp is chosen to amplify the signal, only 7 bits of the 12-bit ADC are effective. Whereas by choosing the TSZ121, which has an extremely low VIO of 5 microvolts, no LSB will be lost when using a 12-bit ADC and the entire resolution of the ADC can be used. So it is not necessary to spend money on a precision ADC if the op-amp is not correctly chosen. As the VIO is principally due to the mismatching of the input components, this parameter will also vary in function of the ambient temperature. So it is important to take into consideration, in a precision environment, the offset drift in temperature, generally called ΔVio per delta T. The VIO is always multiplied by the non-inverting gain of the op-amp and added to the signal amplified by the circuit, which is -100 in this example. And the transfer function is determined by equation 1, where VIO is the maximum value written in the datasheet. Adding the effects of temperature to equation 1 gives equation 2. This allows a fairly accurate calculation of the worst-case change in output due to VIO, neglecting the effect of the resistors. However, the resistor values also change with temperature and will also affect the gain. Typical drift values for general-purpose precision op-amps lie in the range of 1 to 10 microvolts per degree Celsius. In this schematic, VIN equals 0 as the inputs are grounded, so the output of the op-amp reveals the VIO multiplied by -101. This slide compares two amplifiers, the TSV611, a standard CMOS op-amp with a maximum VIO of 4 millivolts, and the TSZ121, a chopper op-amp with a maximum VIO of 5 microvolts. At 25 degrees Celsius, we can see that the TSV611 shows an output offset of -125 millivolts, whereas the TSZ121 is close to 0 microvolts. This shows that if the TSV611 is used in an application requiring accuracy, a calibration must be made at manufacturing level to eliminate the offset introduced by the op-amp. But when the temperature changes, we can clearly see on the oscilloscope that the output offset voltage of the TSV611 changes from -125 millivolts to -90 millivolts. That means when using the TSV611, a calibration also must be made on the temperature at the manufacturing level, which is very costly. By using the TSZ121, which is a zero drift amplifier, we don't necessarily need this calibration phase as the VIO stays very low, even with a large temperature variation, because it exhibits a ΔVio per delta T of 30 nanovolts per degree Celsius. So when the temperature increases by 100 degrees Celsius, the VIO will vary within a range of 3 microvolts. Op-amps, CMRR, common mode rejection ratio. When we speak about precision, another important point must be taken into consideration, the CMRR. The common mode rejection ratio is defined as the ratio of the differential voltage amplification to the common mode voltage amplification. This is measured by determining the ratio of a change in input common mode voltage to the resulting change in the input offset voltage. The common mode input voltage affects the bias point of the input differential pair. Because of the inherent mismatches in the circuitry, changing the bias point changes the offset voltage, which in turn changes the output voltage. Generally, a rail-to-rail op-amp has parallel input stages made of a P-pair, which works on the low input common mode voltage, and an N-pair, which works on the high input common mode voltage. As seen previously, the mismatch between two NMOS or two PMOS is responsible for the VIO, but there is no link between the mismatch of the NMOS and the mismatch of the PMOS. This means that each pair will generate its own VIO. So, depending on the common mode voltage used in the application, the VIO might be different. In a precision environment, the main goal is to achieve the lowest VIO jump when the signal switches from one pair to another. We can have an idea of the impact of CMRR on an op-amp used in differential mode to sense a current through a shunt. High-side current sensing is typically selected in applications where ground disturbance is not tolerated and short circuit detection is required, such as battery current monitoring. The application shows a single op-amp used in a differential amplifier made of the TSV711 op-amp and 4 external resistors. It amplifies the small voltage drop across the sensing resistor of 8 milliohms by the gain RF per RG or 1000, while rejecting the common mode input voltage. First, the battery is fully charged and its voltage is at 4.2 volts. The R load source is 100 milliamps, so through the 8 milliohms shunt, a differential voltage of 800 microvolts appears on the input of the amplification stage. If we consider a perfect world, the input should be amplified by the gain, so on the output we should have 800 millivolts. But despite a lot of effort, we are still not in a perfect world, and some error must be taken into account. As we have seen previously, it is important to take the VIO into consideration. The TSV711, which is already a precision amplifier, shows a maximum VIO of 200 microvolts at 25 degrees Celsius. So on the output, we won't see 800 millivolts, but 600 millivolts. So there is a 25% error due to the VIO. The CMRR due to the mismatch of the resistance must be taken into account, and depending on the precision of the resistance, the CMRR res might be predominant in the total output error. The CMRR of the differential amplifier is given by this equation, and if we consider that the precision of the 4 resistors is 0.1% with a gain of 1000, we can obtain a CMRR of 108 decibels. So, when the battery is fully charged at 4.2 volts, the CMRR due to the mismatch of the resistance will add an error on the output of roughly 17 millivolts. The TSV711 has its own CMRR specified in the datasheet, which is 74 dB. In this case, the TSV711's CMRR will be the predominant one, and it will cause an error of 340 millivolts on the output, or an error of more than 42% compared to the theoretical value. When the battery discharges, the input common mode voltage will change as the schematic shows high-side current sensing. In the datasheet, the VIO is defined at VCC2, so in this case, when the battery discharges, VCC is equal to 2.5. This means that the TSV711's CMRR won't have any impact on the output. Only the CMRR due to the mismatch of the resistance will play a role by adding an error of more than 1%. This table summarizes the impact of the CMRR at different battery voltages when using the TSV711. We can see that when the battery is fully charged, the op-amp's CMRR is the main contributor to the accuracy of the current measurement. We can also clearly understand that the precision of the measurements will change depending on the voltage level of the battery due to the CMRR of the TSV711 amplifier. Let's keep this application in mind, but replace the TSV711 with the TSZ121 op-amp. The theoretical value of the output is still 800 millivolts without any error introduced by the op-amp itself. The TSZ121 has a maximum VIO of 5 microvolts at 25 degrees Celsius, so by considering this error and a gain of 1000, the output will be 795 millivolts and therefore result in an error of 0.5%. As the resistors are still precise at 0.1%, the error on the output is still the same and adds 2.1% of error. In this case, the TSZ121 has a CMRR of 115 dB, so its own impact on the total output error is not predominant. When VBAT equals 4.2 volts, it represents only 3 millivolts on the output, so just 0.4% of the error. As already seen with the TSV711, the main error was introduced by the CMRR of the op-amp. In this case, by choosing a more precise op-amp, such as the TSZ121, which exhibits a very high CMRR of 115 dB, the main error is now introduced by the external resistors. With a VCC equals 4.2 volts, the total error has been divided by 10 using the TSZ121. Moreover, we can also see that with a very precise op-amp, the error on the output will be roughly the same even with a different VBAT, which was not the case when using the TSV711. When the battery discharges, the input common mode voltage will change, and in this case, the resistors are impacted the most, so the error is the same as previously with the TSV711. The power supply rejection ratio, PSRR, and the differential voltage amplification, AVD, are also important parameters when making precision measurements. But the op-amp's PSRR will have a low impact if the power supplies are well decoupled. It is the same thing for the AVD. If the gain of the amplifier is not so high, less than 1000, this parameter will not create any issues. In order to take into account all the parameters likely to have an impact on precision, we can use this equation, where the first parameter expresses the input offset voltage, the second parameter, the AVD, the third parameter expresses the CMRR, the fourth expresses the PSRR, and the last parameter expresses the input voltage drift in temperature. Op-amps, IIB, input bias current slide. In addition to errors in the voltage domain, for example voltage offset or VIO and input voltage noise density or EN, current domain errors such as the input current IIN are also important sources of error, especially for high source impedances greater than 100 kiloohms. The technology used for the op-amp can significantly impact the whole precision of a system. The input bias current parameter, IIB, is defined as the average of the current into the two input terminals with the output at a specified level. The input circuitry of all op-amps requires a certain amount of bias current to operate properly. The input bias is defined by the following formula. CMOS and JFET have a much lower input current than a standard bipolar op-amp. Effectively, for a bipolar architecture, part of the current coming from the current source will flow in the input with a ratio of 1 per square beta. The CMOS transistor is driven by a gate, and there is an insignificant current inside. The small input current that can appear in a CMOS technology is mainly due to leakage of the ESD diode. For sensors with small source impedances, voltage domain errors dominate, while for higher source impedances, current domain errors dominate, especially for bipolar op-amps. The input bias current, even if it represents a very small current, might affect the precision of a measurement, especially when we need to measure a low current using an op-amp. In this application, we want to measure UV radiation using a UV sensor. The UV sensor delivers a small current depending on the intensity of the UV source. A transimpedance circuit is used to convert the current delivered by the UV sensor thanks to the feedback resistance 10 megaohms. The capacitance in the feedback helps to stabilize the system. The UV source is set with an index of 4, and for this level of radiation, the UV sensor will generate a current of 104 nanoamps. This very small current will be amplified by the 10 megaohm resistor, resulting theoretically in an output voltage of 1.04 volts. First, let's use a bipolar op-amp, such as the LM2904. This kind of op-amp might have an input bias current up to 200 nanoamps, or twice the current we want to measure, so it will completely affect the output results. The voltmeter will display minus 0.96 volts, which corresponds to index 1 in the UV sensor conversion table. Now, we can keep the configuration as it is, and just replace the LM2904 with a CMOS op-amp such as the TSV611. In this case, we can see that the output is close to the theoretical value, and the level of output voltage corresponds to UV index 4. In case of an application where the current to be measured is extremely low, or where the input impedance is very high, it is mandatory to use a CMOS op-amp, so as not to affect the measurement. In the precision domain, the TSZ121 is generally the best candidate as it offers extremely good parameters due to its chopper architecture. But the input stage of chopper-stabilized amplifiers does not behave like conventional amplifier input stages. The TSZ121 uses switches on the inputs that continually chops the input signal at 100 kHz to reduce input offset voltage down to 5 microvolts. The dynamic behavior of these switches induces a charge injection current on the input terminals of the amplifier. The charge injection current has a DC path to ground through the resistors seen at the input terminals of the amplifier. Higher input impedance causes an apparent shift in the input bias current of the amplifier, resulting in a higher input bias current than conventional CMOS op-amps. It is hard to find op-amps that can be used across a wide range of source impedances, for example 10 ohms to 10 megaohms, and still achieve DC precision. A comparison of the state-of-the-art DC specifications of CMOS and precision chopper op-amps is shown in the following graph. If these op-amps are used to interface a sensor with certain source impedance, or RS, the resulting offset is given by equation 1. Although the offset performance of a chopper op-amp is better than the rest of the competition across a wide range of impedances, it can be seen that its offset performance starts to degrade rapidly when the source impedance, RS, exceeds a threshold given by equation 2. We can clearly see that if the sensor used has an impedance higher than 1 megaohm, it is better to choose the TSV711 rather than the TSZ121. Op-amps. Noise. Noise is also a key parameter in a precision environment. It is part of life, and we have to deal with it. When an electronics component, even passive, is added to a system, it will add noise that will impact the signal-to-noise ratio. Noise is not easy to understand, as it is non-periodic, and it must be considered using statistics. The easiest approach is to think of it being in the frequency domain, even if engineers generally prefer the time domain. All internal sources of noise contribute to the overall noise generated by the operational amplifier. The op-amp noise is modeled with 3 noise sources. One source for the input noise voltage, or EN, and 2 sources for the input noise current, or IN. A current issued from a current noise source and flowing into a resistor generates voltage noise according to Ohm's law. All sources are physically independent and therefore uncorrelated. 2 other sources of noise can be added due to the gain resistances RG and RF. These noise sources can be expressed as a spectral density in nanovolts per square root in hertz for voltage sources, or picoamps in square root per hertz for current sources, which can be seen as the noise energy at a given frequency, or as an RMS value for a given bandwidth. Let's have a look at each noise source. the noise voltage source in the classical op-amp architecture showing a combination of two different noise types. At low frequencies, generally lower than 500 Hz, flicker noise, also called 1/F noise or pink noise, appears. 1/F noise caused by defects at the atomic level in semiconductor devices. This noise is the main contributor at low frequency. It is generally expressed in nanovolts per square root in Hertz. After the F corner frequency, the voltage noise source becomes white noise. It is a result of thermal agitation of the charges in an electric conductor, and it is also expressed in nanovolts per square root in Hertz. It is the main contributor of noise at higher frequencies. This is why, generally, in the data sheet, the noise spectral density is provided at different frequencies. The current noise source also adds its contribution to the overall noise, especially if the op-amp is surrounded by high impedances. But the input noise current for CMOS input op-amp is extremely small and generally does not affect the design, as it is roughly 5 femtoamps per square root in Hertz. But the input current noise for bipolar op-amp or chopper architectures is in the range of 100 picoamps per square root in Hertz. Resistors will also add white noise according to the equation square root 4kTr. We can see that the greater the resistance, the higher the noise. This table summarizes the different noise sources from a mathematical point of view. The second column represents the noise of each source expressed in spectral noise density, nanovolts per square root in Hertz. As it is a noise referred to the output, it is generally multiplied by the gain of the circuit. The last column expresses the RMS value of the same noise. It is the integration of the spectral noise over the bandwidth of interest. It is important to take into consideration that the output noise is added in a quadratic sum. This equation expresses overall RMS noise on the output. In order to significantly reduce the noise level in an application, it is important to minimize the value of the resistors and reduce the bandwidth, as the wider the bandwidth, the higher the RMS value. This can be easily done by inserting a capacitor in parallel with resistor RF. The cutoff frequency can be calculated to give -3 dB at 5 or 10 times the highest frequency to pass. In this example, we can see the contribution of each source. Here, the noise is expressed in spectral density. To have a better understanding regarding the real impact it has on the output, let's transpose it to a VRMS value for a bandwidth of 30 kHz. This is the noise voltage contribution to the output of the current noise source. This is the contribution of the RF resistance. This is the RG resistance. And this is the equivalent voltage noise source of the op-amp. We can see that the impact of the current noise on the output is negligible compared to the other noise sources. The voltage noise source of the op-amp represents the main part of the noise in this application. We can see that the contribution of the voltage noise of the op-amp is much higher than the other noise sources. However, if no care is taken regarding the value of the external resistor, their impact will become non-negligible. To determine the total error generated by the noise sources, you have to calculate the quadratic sum of each noise source. In this example, the overall output noise will be 5.4 millivolts RMS. Here is an example of a half-bridge strain gauge. The variation of the strain resistance will make a small variation of the input voltage. This small voltage variation must be detected with precision to give a correct value of the weight applied on the strain gauge. Previously, we have seen that the VIO is extremely important for this kind of measurement. But if the VIO introduces a large error, there is still a possibility to calibrate the system and completely remove the VIO. But the noise is a non-periodic signal. and it cannot be calibrated. So for an application requiring precision, it is also important to take noise into account. In this case, the bandwidth is limited to 10 kHz thanks to the 1.5 nanofarad capacitor in the feedback. Let's have a look at the impact of the noise with two different op amps. The TSV731, which is a high-accuracy amplifier, and the TSV121, which is a precision chopper amplifier. The calculation shows the noise impact on the output. For sure, the VIO and ΔVio per delta T must be taken into account regarding the whole error. If the bandwidth of the application is quite large, there is no difference in terms of noise error between the two op amps as they have the same white noise, around 35 nanovolts per square root in hertz. The strain gauge is a DC application, so it is important to limit the bandwidth of the application in order to reduce the noise amplitude. Here, the bandwidth is limited to 20 Hz, thanks to the 795 nanofarad capacitor, which was added in the feedback. In this case, we can see a big difference between the two devices. Effectively, the TSV731 shows a 1/F noise that the TSV121 doesn't have due to its chopper architecture. With the TSV121, the noise impact on the output is reduced by 4. The noise can also be expressed in VPP, and in case of the TSV121 with a bandwidth limited to 20 Hz, the noise will be around 960 micro VPP. It is a first-order noise calculation, as we have to consider a stop bandwidth with a very sharp edge. This means in the worst case, roughly 600 microvolts of error might be added to the output value caused by the noise. This is a summary of the most important parameters to take into consideration when we speak about precision for an op amp. It represents the input-referred error that an op amp might introduce in the whole measurement. And of course, this error must be multiplied by the gain of the configuration. If the op amp has an offset drift-over temperature of 10 microvolts per degree Celsius, it means that if the ambient temperature increases by 70 degrees Celsius, the input offset will increase by 700 microvolts. If the common mode voltage of the application can vary from 0 to 3 volts, and if the amplifier has a CMRR of 80 dB, you can expect a VIO variation of 300 microvolts. And if the power supply used to power the op amp varies by 10%, and if the amplifier shows a PSRR of 80 dB, you can expect a VIO variation of 50 microvolts. Noise is expressed on a 10 Hz bandwidth, and in the application it is necessary to add a sharp 10 Hz filter to consider this 10 micro VPP. Otherwise, the noise must be integrated over the entire bandwidth. The TSV121, which is a chopper op amp, shows very good characteristics regarding all 5 parameters. Thank you for watching this video. For more information, please visit www.st.com/opamp.